Okay. Good morning. Welcome to the panel on space logistics challenges and considerations. We welcome our speakers. Our first speaker is going to be Hao Chen, Assistant Professor of School of System and Enterprises from Stevens University. And we're going to have the Q&A session at the end. So now I leave the floor to Hao Chen.
Thank you for the introduction, and thank you everyone for attending the space logistics session. And today I want to briefly introduce the grand challenge for space logistics and some of the methods that have been worked on to resolve those challenges. Okay, and with those methods, I will also introduce a few case studies, including the logistics to space station, to the moon, and to Mars. So first, when we think about the previous space exploration, for example, the International Space Station, we use the resupply strategy. That means we perform the mission by repeating our resupply to the space station. And when we think about the Apollo program, we have a carry along strategy. That means we take everything we need to the moon. But in the future, when we think more larger scale space exploration, we may have multiple destinations. There are potentially many resources available on Mars, on the moon, and some near Earth objects. And can we take advantage of those space resources? And can we make the space mission cheaper by utilizing them? If so, then how do we design the space mission? So another thing that happened at the same time is the development of space logistics infrastructures. The two most important ones are the ISRU, the in situ resource utilization system. It's like oil field in space. It can generate fuel or other resources to support the space mission. Another infrastructure is the propellant depot. It's like gas stations on orbit. With the ISRU that can be deployed on the moon or Mars to generate resources. And with the propellant depot, we can deploy them on the orbit to as gas station to refuel the spacecraft. And we hope it can reduce the mission cost. So that makes the logistics problem more complex. And we need a new strategic logistic paradigm to handle such challenge to try to reduce the mission cost. It can be a combine of resupply or carry along strategy or some other new strategies. So that's the focus of space logistics. Based on the definition of the Space Logistics Technical Committee of AIAA, space logistics is about the theory and practice to manage the flow of those materials, services, and information throughout the space mission life cycle. So we want to cover both from the early stage mission design and system design to all the way to the operation detailed mission planning when we conduct the mission. So we want to cover the whole life cycle of the space mission. So here comes the grand challenge for space logistics. Suppose we have resources on Earth, right? Because we don't have a factory in space right now. Then everything we start from Earth, and we have some demand on the moon. For example, some habitat, scientific instruments we want to deploy, or the habitat for the crew members or the crew cabin. So that's the source on the Earth and the demand on the moon. First, we need to consider the transportation. How many rocket launches, when, what to launch in mission, and from where to where, and what are the trajectories. Then we need to consider the space vehicle. Do we need a high thrust, low thrust? Then how do we design it? What is the sizing of the vehicle? Do we need refueling? If so, where and when? And third, as I mentioned just now, the infrastructure, ISRU and propellant depots. Do we need depots? Do we need ISRU? If so, what's the size of them? Where should we deploy them? And when should we deploy them? Essentially, everything you see here is something that we need to optimize and design. So we need to consider all those things together. That's a grand challenge that is different from what we did for the logistics on the ground. and also different from traditional mission exploration that we need to consider such a large scale design. So that's the grand challenge, is how to perform effective multi-mission space campaign design, that we need to consider the transportation, the space vehicle sizing and design, the infrastructure sizing and deployment. So in the next, I will introduce two of the methods that I have been worked on and currently still the state of the art in the space logistics field. I want to mainly cover the problem one for the space vehicle design and transportation planning. For the first one, that we use the network flow model. And the next one, the second one is about space resource logistics, focusing on the infrastructure. So first is the network model. So when we consider such a like Earth, Moon, Mars system, we have orbits, we have destination like planet, and we can consider those as nodes. We have nodes as orbits. We have nodes on the Moon, we have nodes on Mars. And if we connect those nodes with arcs, we build a network. And actually those arcs are trajectories. If we can fly from the GEO to the low Mars orbit, that's the arc connected, and that's actually some trajectory for the spaceflight. And at the same time, we can consider the payload, the space vehicle, the crew members, all of those as commodities flowing along the arc. In this case, we can convert the logistics problem into a standard model. We call it generalized multi-commodity flow. So in this flow along the arc, we can consider the commodity gain or loss, which is the propellant consumption in spaceflight. We can consider the commodity type conversion, such as the food converted into waste by the astronauts, or we can consider both of them, such as the ISRU propellant generation. So we can consider all of those. And to make this happen, the mathematical foundation is we need to build a time-expanded network. So the network I show here is a standard network. We only have nodes. We don't have the time dimension. But when we do the mission design, we need to consider the time dimension. So in the time dimension, we consider the transportation arc between different nodes. We have holdover arc along the same node, but at different time steps. The holdover arc is very important. It is the arc that connects the node by itself. It's a self-loop. It's important because we can consider the resource generation or consumption at nodes. Then we are able to consider the ISRU resource generation. It's important. So with this, we can develop our optimization formulation. So I will make the mathematical part, give a brief introduction. For this, I will focus on the case study. So for the formulation, we have a design variable, which is the decision variable for the commodity flow. When should we launch the spacecraft, taking what kind of commodity fly from where to where? Those are X. And we have Y as the flow of spacecraft. And we can build a commodity flow formulation, optimization that can be used to optimize our transportation planning. So the objective most commonly used is to reduce the mission cost, and C is the cost coefficients. X are the decision variables. Similarly for the C prime and Y. So the first constraint at the mass balance, it guarantees that the commodity outflow from a node is smaller or equal to the inflow minus the demand. So it's guaranteed that something can be deployed. The second is the flow transformation. It includes the propellant consumption, the ISRU resource generation. And the third type of constraint is the flow capacity, because we have capacity for the spacecraft, payload capacity, propellant capacity, depending on the size of the vehicle, right? And we also have the flow non-negativity. This is actually the time window. Only when the time windows are open, the space flight are permitted. So time window here are like, we have, for example, we have time window for the rocket launch. And the last one is the sizing model, which is we can consider the sizing model for the spacecraft. Actually, the sizing of the infrastructure can be considered in the capacity or the flow transformation in the matrix Q or H and E. So that's the thing that we can consider all those sizing of the infrastructure and vehicle. So some brief example for the flow transformation, we can write it as the matrix form, and we can integrate the rocket equation depending on the delta V, the S in specific impulse, and the gravity. So we can calculate the propellant consumption. And we can also consider the capacity, the payload capacity, propellant capacity of the space transportation. That's a capacity constraint. So some example of the sizing model. This is an example developed by Taylor. So it considers the field, the structure fraction, specific impulse, and the structure mass. So here I just want to show that even a sizing model as such, a nonlinear sizing model, it can be considered. We can solve it. Another example is the ASRU sizing model. This is for the oxygen generation on the moon. And this is also a highly nonlinear, even non-continuous sizing model that we can still consider together with transportation planning. So if we put everything together, we have transportation, we have space vehicle sizing, we have infrastructure sizing. And as the model I have shown, those sizing are nonlinear. So eventually its problem is a nonlinear programming. It is very hard to solve, and general way to solve it is like the meta-heuristic, genetic algorithm, simulated annealing, but they can never guarantee optimality. And they can be computationally expensive, especially for those highly constrained problems. So one of the main contributions that I have been doing in the space logistics is I managed to make a linear program. So the method to use is the piecewise function approximation, that we linearize through some approximation method by linearize those nonlinear models. Eventually, all the program are changed to the mixed integer linear programming, the MILP method, and then we can solve it efficiently. So here is some brief mathematical background how we can linearize a nonlinear function. If we have a nonlinear function, and we can first define some vertex, and we connect those vertex, then this function, the piecewise linear, is an approximation of those nonlinear functions. And then we consider the union of polyhedron based on those piecewise linear functions, because this is a minimization problem. So, and this is the convex space in the formulation. So the optimal solution should like lie on the boundary of this union polyhedron. Then by define the corresponding continuous variable, depending on the vertex, we are able to linearize some nonlinear functions as the piecewise linear approximation. So we can solve the transportation problem, the logistics problem. Here, I want to show you two case studies. The first one is the Apollo type lunar campaign. In the Apollo type mission, we send a human to the lunar surface. For example, in this case, it's just a problem to show you how can we use this method. We have 10 astronauts to be sent on the moon. Suppose there are 2 astronauts stay on the orbit, similar to the Apollo mission, but a larger scale. And we have habitats to be deployed, which is 3,500 kilograms. And we can do this every year, once a year. And we consider the propellant, the buoy-off, the consumables of astronauts, the crew members, the maintenance. And using the method I mentioned using our network model, we can consider the optimization of such a mission. This is a single mission case. We can design the we can plan for the schedule of the space flight, like when we launch from where to where. And we can perform the sizing of space vehicles, such as the payload capacity, propellant capacity, with the structure mass, depending on the sizing model we have. And this is a result of one space mission case. And if we consider multiple missions together, we have a 3-mission campaign case. That shows the true power of our network model is we can consider the mission together. And in this case, because we have the ASRU model, here we don't have ASRU deployed because it's just one mission. It's too expensive. It does not pay off. But if we consider 3 missions together, you can see we have the ASRU plant 1454 kilogram ASRU deployed at the beginning of the mission, and it will stay on the surface of the moon, generate fuel, and the fuel can be used to support the return flight to the Earth. So that will reduce the mission cost. And we can, at the same time, performing the sizing for the spacecraft for this space mission, 3-mission campaign. And in this case, the total mission of the 3 mission, even including the deployment of ASRU, is cheaper than those 3 single mission cases. And ASRU is effective when we have 3 or more missions. Here is when we have 3 missions, but if we have the 4th or 5th mission, we can still take advantage of the ASRU and have a less mission cost. So that's the power of the logistics method, that we can consider the mission interdependency. We can deploy infrastructure at the beginning. Hopefully, throughout the entire mission campaign, when we have multiple missions, the total mission cost is lower. Then we can deploy ASRU at the beginning. So this is one example for the lunar exploration. And in this case, the computation cost is also relatively low because we only have 4 nodes, like the Earth, low Earth orbit, low lunar orbit, and lunar surface. And we have about 100,000 constraints, and it can be solved in about 300 seconds for those 3 mission campaigns on a desktop. So another case study I want to show is about the space station logistics. So here we want to consider a case of rocket launch delay. It's very common, and especially when we have a much earlier planning date, the delay are typically longer. So that means we have higher uncertainty. Suppose in such a scenario, we have a space station that we are conducting experiments. We want to support experiments. If there's no delay, here is a simple example as a toy problem. We have 100 kilograms for each rocket launch that will support the experiments. If there is a delay, then we have to pause the experiments because we don't have the material. Then the thing we can do is we launch more materials at the beginning as a redundant supply, but that will increase the mission cost. So it's a balance between mission cost and the mission performance. So that's the thing that needs to be handled by the logistics. And this can be done by combining another term when we consider, we call it decision rule, to measure the mission performance merit. And if we combine them together, adding a weight for phi, which is depending on how important or how you want to emphasize the space mission performance, that we can find a balance. And the key is the mission scenario, like the uncertainty scenario in the rocket launch delay. And we have J as the logistics, as I've shown. And we have decision rules and community flow. This is that's shown in the formulation. And we have decision rules. That's the thing we want to find. So suppose this is a space station resupply. We have, for this case, we have 4 rocket launches, and they can be delayed. And we want to have rocket launch every 90 days. So the key part we want to focus is the science instrument and the maintenance spares that will impact the experiments. Originally, if there's no delay, we will launch every 90 days or 91 days, and about 1,000 kilograms of each of them. But it's possible to have rocket launch delay. Then we can define the transportation planning or the decision rule to find a balance. So here we have 2 extreme cases. One is we only focus on the longest delay. It means we want to minimize our experiment time loss. We want to guarantee the mission performance. Of course, that gives us the highest mission cost. We use the initial mass in LEO as the mission cost. And another extreme case is I don't care about the time loss. I want to minimize my mission cost. So we don't consider the delay. If we don't have such a decision rule or the formulation from logistics, we can only pick one of them. But now with the decision rule, we can find the balance between them. And with the increase of phi, which is when we more and more focus on the mission performance, we can reduce the mission performance loss, but we have to pay a higher cost. And those things can be done by the logistics, and the decision maker can pick one point based on their preference for the mission planning. So that's another thing that we can do for the logistics to handle the space station resupply. So okay, the next. Now I just now I introduced the transportation part. The next I want to introduce the resource logistics part, that we emphasize the infrastructure. So the infrastructure here, I'm specifically talking about the ASRU. Previously, when we focused on the ASRU, we are talking about the sizing of it. It's what's the mass of the ASRU, then what's the productivity. But actually, ASRU have a lot of subsystems. we cannot just look at the SRU at system level. It has reactor, it has separator, storage, power system, and each of them has independent interaction with the logistics that need to be considered. And if we consider those, it includes the tree study for the reactor, the power system. We can also consider the operational tree study, like the daytime only operation, or we want to deploy more batteries, or the frequency of logistics, and do we need a larger storage tank? Or we can consider the deployment timeline. Do we need to deploy SRU in one stage or multiple times? Or, for example, if there is a space station, such as Deep Space Gateway, how the SRU interact with it? So all those things need to be done when we consider the subsystem level. So I want to remind you again of the formulation. It's similar to the formulation for the logistics, but now each of the X, which is community flow, is not about the SRU system. It's about each SRU subsystem. One example, for example, the reactor. This is to electrolyze water to generate oxygen and hydrogen. Each reactor, each subsystem, each component is one independent commodity. So we extract the water from soil, lunar soil, and we can do the direct water electrolysis to generate oxygen and hydrogen. And we have productivity, and we can find this is through the transformation in the community flow. Now we can track all of these. But that brings new problem. The problem becomes much larger, right? Because we consider each subsystem independently. So this problem can be computationally prohibitive for the long-term mission. So we propose a multi-fidelity optimization. Well, what we are doing here for multi-fidelity is we think the SRU is only useful, for example, on the moon or Mars, but it's not actually working when we do the transportation. So we consider the SRU at the subsystem level on the moon and Mars, but we consider the SRU at the system level during transportation. It's like a packing, right? We have packing and unpacking. So to do this, mathematically for the formulation, we do the constraint aggregation. We can find the aggregation matrix to combine the constraints together in the formulation to reduce the number of constraints. We also need to do the variable packing to put all those commodities together mathematically in the formulation to reduce the number of variables. In reality, as I mentioned, it's like a packing. We have the SRU packed during the transportation, and we unpack SRU when arrive the moon on Mars and consider the details. And it actually works very well. So the case study first is the lunar mission. Similarly, we want to go to the moon and come back. This time we have a larger mission, and we want to stay on the moon for 120 days. We want to deploy 30,000 kilograms, and with the crew coming back with 5,000 kilograms. We consider the SRU maintenance, the environment on the moon, like the solar irradiance, and we can consider different subsystems. This is the power system of SRU. For this mission, we want to go to the moon and come back. The difference is now we can consider all the subsystems. We have reactor, soil extraction, the storage system, the power system, all of them in detail. And we also have the model, the sizing model for each of the subsystems. And first, the calculation, the computation performance. If we compare the full size, which we don't do the packing, compared with the multi-fidelity that we do the packing, the computation time can be reduced by more than 90%, sometimes more than 95%. So it's very amazing. But the mission cost, which is the performance loss, the accuracy of the mission planning, is less than 2%. So it's pretty accurate with very significant improvement in the computation. And now we can solve more complicated problems. So that's the next case study if we consider them planning to Mars. And you can see this network is much more complicated with all the detailed transportation elements. We can consider the lunar exploration, the lunar base, the gateway, the near Earth object, and the Mars mission. The important thing here is now we can think whether the lunar SRU can be helpful to the Mars mission, something like that, because they are connected as a network. And here we consider two missions. One is the cargo mission to the Mars, which is a one-way mission. We only go to the Mars. Another one is the human exploration. It's a round trip. It's even harder and it's longer. we go to Mars and come back. And for this mission, we can first, for example, we can pick the power system. And we have two types of power system considered. One is the photovoltaic, which is solar panels. Another one is the fission nuclear power. Now we can consider and compare which power system is better to support those Mars missions. First, in the one-way mission, generally the black to solid line is when there is no SRU. The solid orange line is when we have the solar panels. The green lines are when we have the fission nuclear power. You can see for the one-way mission, SRU is not that effective compared with those round trip that we can always get a reduced mission cost. Remember that it's a mission cost in $1 billion. So with SRU, we can achieve significant mission cost saving for this. And when we consider the power system, we can see the fission nuclear power is much better than the solar panels. Remember here, now we are not comparing the performance of technology to technology by looking at the parameters. We are comparing the mission to mission when we have different technologies. We want to perform a system level comparison when we have different subsystems. So it's more convincing and tell us why one technology can be better for such a Mars mission. And besides the power system, we can compare the reactors. The reactor, like using different technologies, as I have shown earlier, different type of reactor technologies like the solid water extraction, direct water electrolysis, and we can have different ways to generate different resources. And those details we can compare in a large Mars mission, which one, keeping other parameters of technology the same, which one provide us a lower mission cost, a better mission performance, and we can pick the one that is most suitable. And the gray line is when we have no ISRU. And we can see with different ISRU technology, we can always achieve a lower mission cost, but different ISRU technology provide us different type of saving. And for this case, a hybrid ISRU system gives the best performance. Because the hydrogen reduction can work well with this to generate more suitable resource. It also depends on spacecraft propulsive modules, such as when we use the engine with hydrogen and oxygen or the methane and oxygen. So all those things can be connected together through the network. And remember that it's not only about the system level comparison. We can at the same time achieve the mission planning, like here. We can always get a mission planning, and we get those system level results at the same time. So using those logistics network or the method, we can get strategic level comparison decisions. We also get operational level details for the space mission. Every time step, we know what the mission is doing. Then we can check step by step what is going on. So that's a attractive part for such a network-based logistics network. So we can solve those problems, giving us operation and provide us the technology selection detail. For example, here, the reactors. So finally, the summary, the goal is to optimize the architecture and the design for the entire campaign. We want to consider multiple missions together. So the first method I introduced, it actually integrates the mission planning and space vehicle and infrastructure sizing. The second one I introduced, the multi-fidelity one, it enables us to consider the details from the subsystem level. So we are able to consider more trade studies and trade-offs in a detailed case. And it will get us for the technology roadmap development. What kind of technology can be useful? So some future research direction for the logistics, we can focus more on the aerodynamics part. For example, here in the case studies, we only consider the high thrust. If we consider low thrust spacecraft, it takes longer for the transportation, but it can be cheaper. But it also brings new problem for the sizing because it's actually harder than the high thrust sizing. We can perform the trajectory analysis. And another part, we can focus on the system engineering, like more dimension, more details on the vehicle design or the infrastructure design. And we can also focus on the uncertainty part, which is the complexity size. This is important because when we have failure in one of the node or some infrastructure or vehicle, it may cause cascading failure in logistics in such a supply chain system. So we want to make it resilient. That's another part we need to focus on. I briefly discussed the uncertainty, how do we handle uncertainty of rocket launch delay through decision rules, but there are much more. So for future of logistic research, because we have more space agencies, we have more space companies that participate in the space exploration, deeper, longer, to support long-term human presence in space, then space logistics is actually becoming more important and increasingly impactful. And another remarks I want to make here is now we have a lot of companies focusing on the on-orbit servicing, assembly and manufacturing, or we call it like in space or servicing, manufacturing, assembly. That is also one important part of logistics. We need to consider the operation. We need to consider the design. So that's a part of logistics, and we need to focus on it to try to reduce the mission cost and make the mission resilient and reliable. Thank you. That's for the my presentation for logistics, and I'm happy to answer any questions.
Thank you, Professor Chen, for your interesting presentation. Now I pass the floor to Dan Evans. He's a graduate student of the American Public University System, and he will be speaking on the logistical facets of prolonged space missions. So, thank you.
Okay, thank you very much. I'm going to go ahead and share my screen here. Make sure you can see it there. Can everyone see that? Excellent.
Yes, we can see it.
Awesome. Thank you very much. So, first of all, I'd just like to say thank you to President Fernandez, Daniel Gutierrez, the American Public University Policy Studies Organization, and Hao Chen. That was excellent. He brought up a lot of great points and some ones that I wish I had thought of, actually. It was excellent. Thank you very much. So I wrote this Blue Moon to Red Dot, the logistical facets of prolonged space missions. And my objective at the time was to discuss and secure resources for systems reliability and safety while exploring the development of a necessary human survival system and infrastructure for a 2.5-year round-trip journey to explore Mars by 2050. I also wanted to inform the reader and potential mission explorers of the challenges that will be faced in the transit and establishment phases of the Mars endeavor. So, with the resurgence of space exploration and innovation, new avenues are being investigated for missions more intensive and with longer durations. In the process of expanding into the solar system, certain modifications to current policy, health, and engineering practices will need to be considered. Mission success is centered around the ability of the explorers to complete their tasks without sacrificing copious levels of health and physiological well-being in the process. In the case of a Mars mission, it is understood that the sheer distance, interplanetary and planetary challenges, they all need to be carefully and meticulously considered, tested, and experimented on to seriously formulate an attempt at mission success. After the first humans flew into space in the 20th century, rapid advances in technology and communication enterprises trickled down to the society at large. This caused a campaign for scientific literacy in the culture, but would only hold significant impact in the popular zeitgeist through the age of Apollo. The Shuttle SLS program would allow astronauts to reach and operate in low Earth orbit. And due to the lessons and experiments learned and expanded upon during this time, along with the resurgence of a new space race, including privatization and commercial contracting, a return to space, a permanent lunar habitat and gateway, and a human to Mars mission, they've all become inevitable, despite the copious risks. Now, these risks include, but obviously are not limited to, the exposure to microgravity, which is known to erode bone density, among other issues, radiation, which can increase cancer risk, extended periods of isolation, which can form psychological issues for explorers, extreme environmental survival, which could put astronaut safety and therefore mission success in jeopardy, and contamination complications, which would lead to forward or back contaminations. The Mercury, Gemini, Apollo, Skylab, and International Space Station missions formulated a lot of integral groundwork for short and long-term spaceflight on the human body, with some missions lasting up to 14 months and yielding crucial understandings of the effects of extreme environments on the human body. Although such missions are necessary to secure practices, policies, and protocols among mission crew and ground control, a situation in which a mission lasting into 21 months is an endeavor unlike any practiced by humans. The use of an external element, such as an orbital or suborbital refueling and resupply station at the Earth or the Moon, would be helpful in securing further mission success for a trek to the Martian surface. Such infrastructure will depend on the budgetary and practical methods deemed most effective by scientists, engineers, policy, and lawmakers. Robert Zubrin, he elucidated an idea of a lunar habitat and gateway in his novel, The Case for Space, in which he envisions a collaboration between private organizations and governmentally funded entities to form cohesive lunar projects. He states that the Falcon Heavy of SpaceX, it can lift 60 tons to orbit, and the lander can take 10 tons to the moon. Two landers would both need to be sent, one for cargo and land surveillance, and one for a habitation module. Both of them would be tasked with building a habitation and excavation area while the first crew is sent to the surface. Now, the best place for some type of lunar base would be at the poles, since the poles have ice and can be mined through electrolysis to make hydrogen, oxygen, rocket propellant. A lunar outpost and gateway can be crucial to Mars' mission because the moon has 1/6 the Earth's gravity and no atmosphere. So liftoff from the moon could be much easier than liftoff from the Earth. If astronauts could launch from the moon, it would save about a third of the fuel needed to get to Mars. So the moon is a launch point for many ideas that the gravity of the Earth has quite literally crushed. Modern science, medicine, engineering, and psychological health practices must all obviously be utilized to further develop and provide a realistic guideline for what future explorers to the Red Planet are likely to encounter and cope with during their mission. Until these aspects are studied and experimented on with more scrutiny and discretion, the ethics of further space study will remain questionable and could lead to undesirable consequences such as mission failure or extraneous spending on materials, principles, and practices. So I'm going to go ahead and just discuss some of the issues we have here. So the coordination of space travel and the inevitable health consequences that will plague travelers continue to cause copious concerns for scientists. These concerns obviously begin with the space race of the mid-20th century, and they'd continue through the years of development. The astronauts in the early days of Mercury, Gemini, and Apollo missions experienced various maladies related to their time in space and the lunar environment. Although methods have been researched and practiced obviating such concerns in many cases, several deadly and/or potentially harmful problems remain. Some of these methods have been proven to be effective solutions for temporary or short-term missions, but solutions to longer duration missions, they remain nebulous. In retrospect, the effects of space travel still carry health risks. And again, these include microgravity, which is known to erode bone density, radiation, which can cause cancer risk, extended periods of isolation, and contaminations. Now, the solutions to the problems found so far, again, can only be considered when a rapid return to Earth will be possible, and therefore can be ideal for LEO, which is low Earth orbit, or even moon excursions. However, a mission to Mars will require far more scrutiny and analysis due to the issues that can compound in the process of reaching orbit, exiting orbit, traveling through space, landing on the Martian surface, living and working there for extended periods of time. Exiting Martian orbit, traveling back, and re-entering our own atmosphere. I've expounded on some of the risks here, and I've extrapolated some potential solutions that have thus far been formulated or put into production. So the first one that I see here is exposure to microgravity. Now, vestibular disturbances can be best classified as symptoms of and pathology of dizziness, vertigo, nausea, disequilibrium, and spatial illusions, which is a feeling of falling, and adverse effects on eyesight. Now, although these symptoms can typically be related to some kind of head injury, it's not rare for astronauts to experience vestibular dysfunction upon returning to a microgravity environment. Upon entering LEO, a loss of gravity, it decreases hydrostatic pressure. So bodily fluids get redirected to the thorax and head from the lower body, which expands head space. And this triggers endocrine responses from the heart, kidneys, and adrenal glands. These adaptive responses cause red blood cells and plasma to decrease in volume, as well as cardiac output changes, which can lead to a peripheral vascular resistance, or resistance in the circulatory system used to create blood flow to organs and tissues. Further disruptions to a copacetic bodily equilibrium and function experienced by Apollo and LEO astronauts include decreased sensory motor control, even upon landing on the surface, visual problems, which can seriously and obviously impair the ability to fulfill mission objectives, and an increased risk of virus shedding and infection. Now, other problems can carry on through the mission and during the duration of the stay, depending on the mission objectives and allotted time for mission completion. This was observed particularly through the astronaut program of Apollo, in which astronauts consumed less food than was required or requested during the mission. There were also instances of post-flight dehydration and weight loss, as well as a decrease in tissue oxygenation, particularly during short duration flights upon the return of the astronaut to the surface and with a reintroduction to the gravity of Earth. Now, these problems are not without some form of a solution for the short term, and it is worth noting that policies have been enacted to mitigate these effects for astronauts and maintain an ethical framework. However, these policies, they need to be updated for a long duration mission lasting several months to a year. With a situation like post-flight dehydration and weight loss, or even bone loss and radiation exposure, full or at least partial recovery on Earth is typically sustainable within a brief time. However, the consideration of recovery on Mars must be noted due to its weaker gravity, and therefore a potentially longer and more arduous recovery time may be required. There have also been accounts of the loss of red blood cell mass at a range of 5 to 20%, and post-flight orthostatic intolerance in 100% of crews, and that's dizziness and imbalance. Again, this causes impediments and detriments to mission completion. But nonetheless, one of the biggest and most nefarious issues with prolonged spaceflight is bone loss. Bone loss is detectable after a month in spaceflight. Regional bone loss in weight-bearing areas continues at a rate of 1% per month, and the cumulative bone loss increases with the duration of spaceflight, with sustained loss of bone calcium and muscle nitrogen. Artificial gravity to mitigate the effects of bone loss has been used. It's a potential antidote outside of physical training and resistance exercise, which astronauts are required to participate in. The development of an artificial gravity research system has been a topic of discussion for some time, and experiments with artificial gravity and bone loss in a synthetic gravitational environment have been conducted by agencies such as the Japan Aerospace Exploration Agency, or JAXA. However, there remains engineering coordination to consider with such a project. This would include vibrations and general noise, as well as mechanical complications. It may be possible for artificial gravity, once able to comfortably be utilized, to act as an acclimation tool, slowing down the rotation of a revolving centrifuge during trip, and then speeding it up as the craft approaches a planet. Such prospects remain in question and require further study. Astronauts have traversed LEO and the lunar surface and returned from microgravity environments to Earth and a gravitational pull that the body has evolved to sustain, right? It shows eventual recovery. The problem here, and problem with Mars, is that there are typically relief crews ready to assist the astronauts in the readaptation to the surface pressure and gravity upon landing on Earth. The fact that there will be no relief crew or ground crew to assist astronauts upon landing on the Martian surface, nor will there be any immediate relief from gravitational restrictions, is a problem that, again, we must consider. Despite landing on Mars, which is a planet with a slightly stronger gravitational pull than that of the moon, the explorers will still technically be in a hostile environment, and the gravity felt will only be as strong as 1/3 of that of the Earth. The same gravitational issues can persist through the trip on the Martian surface, albeit potentially at a less drastic rate. During flight and the mission, health must be continuously monitored, obviously, to identify and predict health threats or some kind of system malfunction that could alter the course of explorer health and well-being. In almost any case, the self-sufficiency of the crew will be of utmost importance, considering the distance that is incommensurate with a rapid return or resupply. The second aspect that I wanted to discuss is the radiation. Galactic cosmic rays, or GCRs, are highly excited energetic particles from outside of the solar system that continuously bombard Earth and are formed by events such as supernova. Prolonged exposure to GCRs can pose a lifetime risk for cancer and cataracts. Other negative physiological effects can also happen in the exposure to solar particle events, SPEs. Although some solar particle events are emitted, solar particle events are emitted from the sun and can theoretically be shielded from, GCRs are copious and they extend from all directions into space. Each of the Apollo missions, they took place between the solar particle events. Radiation exposure has been and will continue to be dependent upon shielding, timing, and crew selection. And regardless, one cannot simply rely on fortuitous timing of the missions to the lunar or Martian surface, simply because these missions will be of much longer duration than those of Apollo, and SPEs are unpredictable. Therefore, shielding will be the number one ionizing radiation mitigation tool. It is worth noting that cosmonauts have spent 1.5 years in space and have recovered well upon return to Earth. Among astronauts in the Apollo program and the LEO missions, radiation levels were higher than expected. An LEO low Earth orbit exposes a crew to 10 times the radiation than that is typically absorbed by people on the surface of the Earth. The short-term effects of ionizing radiation include memory loss, immunity issues, heart disease, stroke, and blindness. And long-term effects include cataracts, sterility, dementia, and cancer. Exposure to GCRs can pose a lifetime risk for cancer and cataracts, as I said earlier. And recently, a radiation assessment detector was utilized and showed prolonged spaceflight could equate to a 20-year reduction in lifespan. One may believe that upon settling on the lunar or Martian surface, such exposures will be significantly radiated or palliated, and the lunar soil is irradiated with ionizing energy due to its lack of a strong atmosphere and constant radiation bombardment, and it can emit neutrons. Furthermore, the Martian atmosphere is unlikely to shield from harmful radiation, nor does the planet maintain any strong magnetosphere due to its size. Ethically and logistically, it is important at this point to understand exactly what the explorers would be dealing with in terms of the physical space that they are at once they arrive. So first we talk about the Martian environment, right? There appears to be some form of misconception that I've noticed some have upon being on Mars. The misconception lies in the idea that you're no longer in space because you're standing on a planet that exerts a gravitational pull and it has an atmosphere. And that's technically true, but the difficulties that one encounters in transit to the Martian surface still exist to many degrees due to the lack of air, radiation bombardment, and low gravity. So as I stated earlier, autonomy will be of the utmost importance for the crew. And it's because Mars is 34 million miles away, about 136 times further than that of the moon. And this means communication delays are inevitable, some being 20 minutes or even longer, obviously. Even after traversing such a vast distance, the Martian atmosphere is replete with unbreathable carbon dioxide, making fresh air unavailable. In November 2013, the Mars Atmosphere and Volatile Evolution Mission, or the MAVEN, was launched and arrived at Mars in September 2014. The mission was to measure the upper atmosphere of Mars, the interactions between the sun, solar winds, and the atmosphere, and the rate of gas loss from the upper atmosphere into space. Now, this was an effort to understand the role that such atmospheric losses played in climate change on the Martian surface. The mission yielded that the Martian atmosphere is primarily made up of carbon dioxide, along with molecular nitrogen, argon, molecular oxygen, and carbon monoxide. Due to extreme ultraviolet radiation flooding from the sun, the atmosphere was eventually eroded after the loss of the Martian magnetosphere, which happened approximately 4 billion years ago. Hydrogen atoms escape into the atmosphere after being carried away by galactic cosmic rays due to the light atomic weight of hydrogen. It's widely accepted that the Martian surface was once host to liquid water. However, only a fraction of this water can be found frozen in ice or among the water-rich minerals on the surface, including dune flows and slope streaks, the obliquity of the geomorphic representation, or glaciers at the poles. The possibility of subsurface water remains constant and is seen in 2016 by NASA as the discovery of a large amount of underground ice. And in 2018, Italian scientists found a subglacial lake. Each aspect of the Martian surface, atmosphere, and ecology must be understood and meticulously studied by ground control scientists and researchers, as well as astronauts, before the undertaking of an in situ mission can be considered. And from here, I move on to the psychological effects and crew considerations. Behavioral health and performance of space crew members is currently a substantial issue, and it also needs to be studied further. Now, the astronaut, whether in flight or out, will be a crucial operator and a critical decision maker during the mission. Now, although physical maladies such as acceptable radiation levels vary on a case-by-case basis, the psychological selection of astronauts can be supported by selecting in methods, which would identify candidates who can adapt to demands, the stability of motivation over time, interpersonal compatibility among the crew, and the ability to cope with stressors. Certain requirements should be made clear to crew and mission commanders. For instance, space station commanders should be able to give crew direction about work tasks, offer emotional support, and provide sensitivity to crew adaptation. And in this case, there should be little confusion or contention on the duties of each individual crew member, including those leading the command. There are a few basic conditions that contribute to the human ability to perform. Such conditions include sleep and circadian rhythms, which influence clarity of thought and psychomotor aptitude, behavioral health and cognition, which maintain a healthy brain that is not damaged or subject to behavioral illness, psychological adaptation, which could avoid negative working environments, and human-to-system interface, encompassing the sufficient pre-flight and in-flight training, as well as work schedules that don't require too many tasks to be performed at once. The effects of isolated and confined environments include cognitive impairment, time sense disturbances, motivational decline, sleep deprivation, psychosomatic symptoms, anger, anxiety, depression, and social conflict. Isolated and confined environments also can show adaptation, elation, adventurous feelings, and satisfaction. So there's good sides to either of those. But either way, group dynamics will need to be considered, as well as the division of labor, interpersonal communication, crew member adaptation, and resource management. If not, crews fragment or displace anger and tension in the isolated environment onto their own or onto their fellow crew members, which obviously leads to serious mission jeopardy. Crew rapport is also important because habitability issues occur and must be dealt with in close quarters, obviously. Stowing items, waste disposal, excessive noise, hygiene, and the maintaining of crew health while adhering to individual and cultural customs, as well as a need for privacy, will also need to be considered for long-duration missions. For astronauts and explorers hoping to traverse the stars and eventually make a new home on the lunar or Martian surface, rigorous training is required. The schedule should include familiarization with medical and physiological problems in microgravity, cardiovascular deconditioning, radiation exposure hazards, countermeasures, habitability, and the use of in-flight medical equipment. There's also the possibility of contamination. Planetary protection, as we name it, is defined as a set of guidelines that aim to prevent the forward contamination of celestial bodies with biological material from Earth and backward contamination of the terrestrial biosphere with extraterrestrial biological material. Back contamination risks include those involving the return of any material collected on surface, as well as vehicles, people, equipment, and other Martian material. The environmental economics deals with the interactions between economic behavior of humans and the quality of the environment. If back contamination were to occur, this would be considered a threat to environmental assets due to the risks of negative backward contamination. Therefore, fewer precautions are likely to be taken with forward contamination, and back contamination practices are to be scrutinized. Various public groups will review the information regarding back contamination and, if needed, challenge the policies for such issues in the courts. And finally, I'd like to talk about briefly policy and further recommendations. As I said, with the Apollo missions, to the moon in the late 1960s, an official policy was necessary to regulate the potential for contamination of sources on the moon and on Earth. And in 1967, a policy was put in place to control the possible contamination of planets by microorganisms and other organics during planetary missions. It was accepted as official policy by the Committee on Space Research, COSPAR, of the International Council of Scientific Unions. The policy lays out frameworks and guidelines for current and future excursions in space and practices for planetary protection. Now, these guidelines are always changing due to added information constantly found through exploration. In the case of a Mars mission, a method of gathering and garnering public support called participatory technology assessment has been recently developed and utilized to understand public preferences to inform governmental regulations, policies, and decisions. In the case of the current PTA use, the public was given information about potential Mars missions for NASA, including one in which a crewed mission was sent to land and control robotics on the surface, a crewed mission to the surface for an exploratory and short duration and a permanent settlement. The crewed orbital robotics mission showed the most promise among citizens. It's possible that such a technique of data collection could be utilized for future Mars missions, and thereby it can inform governmental decision-making. However, this will need further development and understanding of the effects of deep space exploration. So finally, I'd like to come to my conclusion here. Since the dawn of that space race and the creation of NASA, the physiological and psychological effects of the extreme environment of space have been under study by scientists and engineers, and the effects of microgravity and radiation have proven to be serious deterrents in the future of humanity in space for prolonged periods of time. But with technological and medical innovations, new prospects and opportunities for further study have been introduced to scientists. Although the long-term effects of prolonged space travel are understood and accepted, the period and recovery rates tend to vary among case studies. The environment of Mars is unforgiving and not conducive to human health. For long-term or even mild exploratory missions to occur, habitation and supplies will need to be sent prior to human arrival and occupation. Even though astronauts have relied on ground control for support in the past, the distance makes communication lag, emergency resupply, and crew extraction impossible. The ability of the crew to be self-sufficient is, again, of utmost importance. Due to the studies and analyses done through missions on the ISS, scientists have been able to discern relevant conclusions to what prolonged spaceflight missions can do to the body of the astronaut. Recovery times vary, but the symptoms remain in one way or another. Psychological issues remain under study, although certain issues that have been observed in the past can hinder crew rapport and even cause mission jeopardy. Public support will be necessary to build a Mars program or a lasting space program of any kind. With new policy and support from government agencies and private corporations, a realistic mission to the Martian surface could garner public support. If only the astronauts and explorers, as well as their families, are completely prepared for the logistical issues of traveling such a vast distance and settling for at least a few months in such a hostile environment. For now, it may be prudent to focus on a lunar outpost and base camp before traversing the vast distance to the Martian surface. Due to the distance in time and space, unforgiving environment, unbreathable air, and radiation content of the planet, the resources used to form a Mars settlement could be repurposed to fit a moon base. Once the moon base with a quick emergency return timeline, less communication lag, and familiarity with the surface morphology is established, the technology utilized to make such a prospect possible can be remodeled for a future Mars mission. And this is assuming humans can counter the effects of an approximately 21-month excursion into an isolated and confined environment by the time such a mission is proposed and adopted. And so that's it. Thank you very much.
Thank you, Dan Evans, for a really detailed presentation. Now we can open the floor for questions, or if you want to discuss between yourselves about your presentations. We still have 10 minutes.
So I think saw some questions in the Q&A on the website of the conference platform. Maybe we can address that.
Yeah, go ahead.
Yeah, it's not in the Q&A on the Zoom, but it's in the section on the OVA section website, I think. And the first one is, how can we establish supply chains and infrastructure in space to support long-term duration missions such as lunar or Mars exploration? I think this is more relevant to my presentation. For those long-term mission, as I discussed, it's a short answer. It's mission interdependent. When we have just one mission, we deploy the infrastructure. It's not that efficient because it's very expensive. But when we consider multiple missions, for example, 3 lunar missions as a result I have shown, it's worth to deploy the infrastructure because it will pay off eventually. Even though it's very expensive, but we generate resources, so eventually the total mission cost is lower. So for those long-term missions, we have to consider mission interdependencies. Previously, we don't because they are short. For example, Apollo mission in total is 13 days. If it is a few years, we have to consider those connections. The second question I think on the website is, what are the potential risks and mitigation strategies for space logistics, including issues such as collision avoidance, space debris, and system failures? So this is also relevant to the planning I discussed. So for the collision avoidance, it's more like operational level thing. But for our logistics planning, we focus on the system level. When should we fly from where to where? But those debris avoidance in the space flight, for each of the flight, they are more about GNC thing, like guidance, navigation, and control. That's not the thing that we focus. We focus on the system. But for the debris, we can consider active debris removal. It's not about how can we remove one debris, it's control problem. It's about how can we plan a mission to remove 5,000 debris. The design of the servicer, the planning of the mission, and how should we schedule those missions. That's a system problem. So that's something we focus on the logistics. Actually, I have active project from NASA focusing on the active debris removal at the system level. And the last component of the question is about system failure. I discussed like one example I've shown is the redundancy. When we have some rocket launch delay risk, then we can have some redundancy supply. It will increase the mission cost, but it can mitigate some of the risks. But redundancy is not enough by itself. It's not that efficient because we have much higher mission cost. So there are much more things to be done in logistics. We have to handle such a failure. This is a good question. Like, it's important. And this is also the current focus of logistics, how to handle those uncertainties. And the third question I see on the website in the Q&A is, maybe this is for Dan to answer, is how do you suppose we will mitigate the bone loss during the prolonged destination to Mars?
Well, they already have a few methods of doing that in terms of just copious exercise. Astronauts have to exercise at least twice a day for, I believe, 2 hour and a half. That's partly what partly what will help them mitigate the bone loss. Otherwise, I'm not totally sure about that, to be perfectly honest. I mean, maybe how you've come up with some answers on that, but the only thing that I can think of is really just in order to maintain bone density, you have to find ways to continue to put pressure on your system.
Yeah, on space station, actually, astronauts do exercise. They have a scheduled time for exercise. This is also try to make it the bone loss. But actually, Dan's presentation make a good point. My research currently focuses on the robotic part of the logistics. The human part is also very important. That is also the new trend for logistics to consider the human. And the last question I've seen is also, I think it's also relevant to Dan's presentation, is how, it's a long question, is how might modern advances in robotics be able to mitigate some of the risks posed by a lack of relief crews? these technologies are being developed for Earth-based care for those with disabilities and elderly who often face similar mobility issues or psychological limitations due to the fragility. Like, how do we handle such the lack of ways to relieve crews?
Ways to relieve crews upon landing on the surface with AI?
The space mission, like mitigate some of the risks posed by a lack of relief crews. Like there are some technologies on Earth, what about in space?
I understand. Yes. Well, I was actually thinking about this recently because we have this resurgence of AI that's sort of been coming into the mainstream and has been really either feared or loved by different groups of people, depending on which one you belong to there. I think that there is a possibility that we'll be able to use robotics to assist crew members upon landing on surfaces after prolonged missions. There's also something really fascinating I've heard, and I included it briefly in my paper, but there was an idea that you could slow down you could have an artificial gravity system, right? And in order to do that, you would have to have centrifugal motion. And then you could have that centrifugal motion, you could slow it down during the duration of the trip. And then upon reaching the surface or the last few, however much time of in between transit, once you reach Mars, you can speed it up again so that you're slowly reinculcated into a gravitational environment. And therefore you would have less of a lag time in terms of reinculcation into a gravitational environment, despite the fact that Mars doesn't have our gravity, but it has enough to make, I would say, relief very difficult upon a 8-month journey there.
One thing I want to add, actually, in Dan's presentation, he mentioned the team dynamics, the group dynamics between astronauts. That's another thing that we need to consider. Like it's important for the emotion factors in the astronauts, their interactions, and that's a part that we need to consider at the design level, at the initial design in the team composition. We need to consider this is also related to the failures. We have system failures. We have the risks on the human side. The fatigue, the sleep loss, those are very common in space. How can we handle this for those long-term missions? And all of those need to be considered together, which this is actually part of the logistics, not only for the materials, robotics, also for the human. Great answer. Thank you, Dan.
Yeah. It's extremely important too, because communication lag is going to last anywhere from, I believe, 20 minutes to 8 hours. And obviously, because Mars is going to be on the opposite side of the sun, again, crew sufficiency by itself is going to be extremely important. So I think that you would need to find it's going to take a very unique group of people to be able to handle system interface as well as such isolation. If something goes wrong, say you're out traversing the surface of Mars and something goes wrong, you break your leg or whatever happens, or you run low on something, there's some type of accident, you may not have very much, you may have only, depending on where the planets are aligned, your communication is significantly diminished with the surface of the Earth.
Yeah, that's a good point. Communication lag actually also adds more pressure to the crew activity. And if something happens, like it's also about failure, then the crew have to deal with it by themselves. So it's another type of pressure which may impact the crew performance. I see a new question. Is anyone seriously looking into the use of biologic or robotic adventures that could be launched, landed, and then controlled from Earth? We obviously have rovers, but something more resembled the human.
Yes, they are actually. From what I understand, it's still in the infantile stages, but from what I understand, they are working on formulating robotics. I think what the plan is for that as of right now, and I can't speak too much on it because I don't have all of the details, but I think what they were hoping they could do is they could try to keep a crew in orbit and then send robotic missions down to the surface and use the robotics from there. But I'm not sure if you've heard anything about that.
Yeah, it's something that is actually beyond the logistics part. It's more like a operation detail for those.
Yes.
And it's also related to the technology development, right? It's beyond what we can do for the planning itself. For the logistics, we focus on the planning based on existing technologies. But for those robotic or biological vendors, it's more about the technology development. And if we have it, it will be helpful. But right now, we also need to think about how do we rely on those human and robotics, most likely based on the system itself, not in the humanoid robotics, something like that.
People are congratulating you for your excellent presentations. Thank you very much, Hao Chen and Dan Evans. We really enjoyed listening to you, and hopefully we'll see you in future conferences.
Thank you.
Thank you very much.
Have a
Thanks.
great day.
Enjoy the conference.
Bye, guys.